Hi, my name is Ingmar Poese. For those of you who don't know what an LPM is, that's the longest prefix match, which means a little bit first about myself. I'm a network nerd. What I do is networks. I do IP addresses, v4, v6, doesn't matter. I do analytics on networks, and I have done that for about 10 to 12 years now. I work for Benox, and we do, surprise, surprise, a lot of network analytics. But what Benox is actually about, or what we started off as 3 years ago, is if you have servers on the internet and they deliver content that is suboptimal because of various different reasons, we build software that gathers network information and does exactly that. It balances traffic, it reduces link loads. Now, when you gather traffic from networks, you get a lot of it. This is one of our deployments that we currently run. Just as a sort of short introduction of what we're actually dealing with here, the very left column is the network data that's actually flowing into our system that we currently have. Most importantly, since we are going to talk about LPMs here, most importantly is the BGP feed, which comes from over 200 different routers at around 70 million entries per hour. And the other one that is very important to us is the net flow, which is sampled data about the traffic at pretty much all of the routers. This one totals at around, what did I write here? Oh, that's a B, okay. That one totals at around 2 billion records per hour, also coming in as streaming data. Now, we don't do live analysis on this yet. We are not that far in our ClickHouse deployment at this point. What we do is we write to disk and we load afterwards for the entire hour. So we do batch processing with ClickHouse. The main problem with this is when you have the NetFlow records, what you want to do is you want to convert the IP addresses found in those, so source IP, destination IP, you want to convert them to some sort of prefix, so you want to aggregate on that. And preferably you want to aggregate further onto AS level or even further onto sort of neighboring ASs. Anyway, what we're doing in the end is we're feeding all of this into a pre-processing. Like I said, we can't do it in ClickHouse Live yet. That's why we have the pre-processing. That one reduces everything down and then puts that into ClickHouse, where we do the actual processing, which then gets sent over to another ClickHouse instance, which is mainly there because one of them has to be in a confined data center. The other one can be in the public cloud. And out fall nice traffic statistics, as you can see them on the top right, about what happened in the network, where, at what point in time, what traffic flow went through what router, and so on and so forth. Back to the actual problem. We have subnets. These are coming in from the routers. I just took two example subnets here. 8800/16 and 8880/16. They both belong to Google, if I'm not mistaken. And the second one I see should be a 24. So there's a mistake in the slide. That actually works. This one should be a 24. We explode that one out, so we convert the IP addresses over here into their integer representation. We try that with both functions. ClickHouse offers conversion functions for v4 and v6. We try that with both functions. For the subnet 4, this actually works. Subnets for v6, this doesn't work. It just returns a 0, means conversion failed. We don't want to look at that anymore. But since this is supposed to be agnostic for v4 and v6, we do both anyway. If you throw in a v6 subnet here, this one would be 0, and this one would hold the actual integer values. Got to be a little bit careful here. v6 addresses have 128 bits. Biggest data type in ClickHouse is an int64, so this actually needs to be cut to the first 64 bits, which is the only relevant part for routing anyway. So then we build an array out of this, which has exactly two values, the v4 first and the v6 afterwards. We do this again. We remember this is the v4, this is v6, and here's a CIDR mask. There's the correct one. We have a CIDR 16 and a CIDR 24. This goes on. We now throw away all the redundant information that we don't need anymore. So everything that was v6 related now disappears, and the only thing we remember is that were the integers for the respective subnets. This was the IP version, that was the CIDR mask, and we just tag this one along for later things. Of course, at any point in time, additional information, like for example timestamps, AS path, next hops, and so on and so forth, can also be tagged along. That doesn't really matter to the process. Now, that's one half of the problem. The important bit here is these numbers. That's why I made them red. Please remember them. I will query on them in about a minute. The other part is we actually have a stream of incoming IP addresses. We do the exact same thing as we did before here. We have a v4 and a v6 conversion. v6 again fails with a 0. We put those two in arrays. We remember the protocol version. We go ahead, we remove the ones that we don't care about, so what's left is the actual IP address as an integer representation and the v4, and we remember this number. Now, if you remember the other two numbers, you'll figure out that these numbers, that the numbers that we just had actually don't match. So we cannot join these together. There is no way currently how we can figure out which subnet that we have over here actually this IP address falls into, especially with the longest prefix match. And this is the point that I was actually kind of going a little bit to lobby for. If you have a type that actually supports this kind of data type, and that has an operator that is capable of saying that this IP address belongs to this subnet and to this subnet, then you would already be done, and you could just do this in a join. But currently you cannot. So what we need to do in this case is we take the IP addresses and we explode them. v4 addresses get exploded to 33 entries, v6 addresses get exploded to 65 entries, and what comes out of this, if you do it right, is, if you haven't spotted it, this number is exactly the number up here, this number is exactly the number there. You can use your join again at this point, and after that, you actually have your matches, which means this IP address matches these two subnets. Only problem here at this point, like I said before, v6 means you explode the table by a factor of 33, v4, sorry. v6, depending on whether you just use the first 64-bit or the full byte, you explode the table by either by a factor of 65 or a factor of 129, which is going to blow up your RAM. So on large tables, this at the moment, unfortunately, doesn't work. There are a few more caveats to this. One of them is that even if you do an any join on this, it will return both of these entries for that IP address. So you need to sort afterwards by a descender in descending order, and then actually take the first one. Or you do this via a group array that also works. So in summary, LPM does work in ClickHouse, and it is possible. Actually, this is still faster than doing it through a lot of other tools that I tried doing this with. The only problem is the RAM. Luckily, currently on the machines, we have a lot of it, but even as the tables get bigger, this is not going to be very, very quick or very efficient on the resources. And I think that's already it. I hope I didn't overstretch. I also started a topic about this in the Google groups. If you can't type fast enough, just search for LPM. There is also the full example query in there to actually do this on ClickHouse, including the table schemas if you want to do LPM in there. That's it. Thank you.